Thank you, Vivek. And our final tech talk before our next networking break is on how growing requirements on temperature sensors can be met by Dr. Ing Christoph Nick, Head of Advanced Development at Nexensos GmbH. Dr. Christoph Nick, please go ahead.
Welcome to my presentation about how growing requirements on temperature sensors can be met. My name is Christoph Nick from the Heraeus Nexensos. What can you expect within the next 15 minutes or so? First of all, I prepared one slide about us as a company, who we are and what we typically do. And then we're going to jump right into, and I'm going to explain to you a little bit about temperature sensors in general, and then about resistance temperature detectors, or in short, RTDs especially. And then I will finish off with our latest innovation, our microRTD, our solution to push the limit and to go smaller and smaller. Now let's start. So, as I mentioned, we are the Heraeus Nexensos, and we are experts in platinum thin film temperature sensors, measuring or covering a wide range of temperature going from -200 to +1000 degrees Celsius. And those temperature sensors, they can be found in all sorts of applications, ranging from the mobility sector, in exhaust gas applications, or e-mobility in the charging or battery applications, also in the consumer area, in consumer electronics or appliances, and also in health, like medical lab equipment, or in the cold chain, which has increased popularity due to the pandemic that we are still facing. And then finally, those sensors are also applied in industrial applications such as the energy and power sector, or HVAC and process technology. And in many of those applications, we see a strong trend of growing requirements for smaller and smaller sensors, because miniaturization is just something that drives innovation quite a lot. And in my presentation, I'm going to show you some basics and also want to show off the restrictions that we are facing. But before we start with the RTDs, or resistance temperature detectors, I just want to give you a little overview about different technologies that there exist to detect temperature. Now, first of all, we have the RTDs that I've mentioned a couple of times now. It's basically an electrical resistor that is strongly temperature dependent with a positive temperature coefficient. That means the electrical resistance will increase with increasing temperature. Its properties are that it's very linear, it's highly accurate, and has a high long-term stability. And also, the application range of temperature is quite wide, ranging from -200 to 1000 degrees. Then next to it, we have the negative temperature coefficient thermistors, or in short, NTCs. It's also an electrical resistor that has a strong dependency of temperature, but has a negative temperature coefficient, and because of that, high resistance at low temperature, which is then steadily declining with increasing temperature. The properties of those NTCs are that they have a nonlinear response, a high accuracy, and because of the nonlinear response, you need a lookup table is required. The typical application range goes from -50 to about 250 degrees C. Then third, we have thermocouples. It's basically an electrical junction of two wires of different metals. And on those junctions, we can use the so-called Seebeck effect with the voltage drop and use that as a sensor signal. Here as well, the answer is nonlinear. We have a low accuracy and also lookup tables required. But the great benefit is that it covers a huge temperature range, going from -200 to up to 1750. And then finally, we have the PN junction or diode. It can also be incorporated into integrated circuits or ICs. And here we have a linear response, low accuracy, a slow response, and a typical application range of -70 to 150. Now, the great benefits of RTDs are, as I said, the linear response over a wide temperature range and its accuracy and the long-term stability. And that's why I want to focus on those, and also because it's our home turf. Now, how exactly do those RTDs work? As I mentioned, they are basically electrical resistance, which is defined by some parameters that I'm going to show you and explain here on this slide. So we have the specific resistance rho of the material that we are going to use, and then the wire length and the wire cross-sectional area. Now I call it wire because that's one method to create such an RTD. The other method is to go planar and structure a meander on the substrate, which is shown at the top right side. Now you can change those three parameters to adjust your resistance. Now you can increase the length of the wire or the length of the meander, and with that you will also increase the resistance. Or you can decrease the cross-sectional area, and with that also increase the resistance. Or the third option is to change the material, and with that the specific resistance rho, and that will also change the resistance value. Now, with this trend, with these growing requirements for smaller and smaller elements, it becomes clear that you can't fit an infinite large resistance onto a given surface area. So the length L is quite limited. And so because we only have some options for the materials, which are some of those are shown at the bottom left side, we are left with the parameter A, the cross-section area, which are the critical dimensions. And those are limited by the technology and also the materials, such as the substrate that we are going to use. And these are actually the restrictions that we are facing today with the standard technology and standard materials. We are pretty limited with the smallest dimensions and the smallest dimensions of our RTDs. Now we have a resistance, and it's very beneficial to have a large resistance, but we don't have a dependency of the temperature yet, so we don't have a sensor. And now some physical properties of any metal comes into play, the so-called temperature coefficient of resistance, or in short, TCR. The TCR can be explained by the so-called Callender-Van Dusen equations. One of those are shown on the left. You see here that the resistance is dependent on temperature, and you see the R0 as kind of the base line. That's the resistance at 0 degrees Celsius. And then you see some parameters. In this case here, alpha and delta. If you go to temperatures below 0 degrees Celsius, you also have a beta coefficient. But the alpha coefficient, that's what we refer to as TCR. And this is also equivalent to the mean slope between 100 degrees Celsius and 0. And if you go ahead and plot those curves for different R0 values, and I've done that for platinum in this case, you see that with an increasing resistance, you will also change the slope of your curve. And that means for every Kelvin or degree Celsius in change of temperature, you will have a higher change in resistance, which is also beneficial for measuring. And that's one of the reasons why a high resistance value is desired. And I summarized it here at the bottom. So if you want to have a large slope or a high slope, then a high value of R0 is desired. You can also obviously change the material, but again, as I mentioned already in the previous slide, there are some restrictions to that. Now, these are the conflicts that we are facing. So, yes, we want to have a very large resistance value, but we also want to become small. And how can we match those two requirements that we want to achieve? Now, we did that in our latest innovation with a change of material, and with that, the change of technology as well. So we developed a polyimide-based temperature sensor that has a very flat surface area, and with that, we were able to decrease the critical dimensions quite significantly. And because it's polyimide-based, it's also extremely thin. It's only 50 micrometers, so roughly the diameter of a human hair. And we can go down to footprints of 0.6 by 0.3 millimeters, which is a standard chip size, the size of 02, 01. We also have 04, 02 chip size available, which would be 1 millimeter by 0.5 millimeter. And we can fit 1000 ohms or 2500 ohms onto that tiny surface area. And how they compare to our standard product portfolio, like the standard larger components, this is shown at the bottom, and you see how tiny they are. I think it becomes also clear with our nice picture here with the matchstick. Now, as I said, it's polyimide based, it's very thin, and with that, it's also flexible and bendable, at least in some boundaries. And we can cover a temperature range of -40 to up to 130 degrees C. Application areas of this component are as wide as our standard components as well, ranging from advanced electronics and advanced packaging, because they are so thin, you can actually laminate it in between layers, going to lab-on-chip like microfluidics, on-skin temperature devices, lifestyle applications, wearables, or again, the automotive sector in EV charging and battery monitoring applications. What are other properties of this microRTD? Again, this is a layered polyimide encapsulated RTD. It's metal-based. It's not a platinum sensor. This is aluminum with a high TCR of about 4000 ppm per Kelvin. And the bonding pads are nickel gold, so you can apply state-of-the-art standard connection technologies, such as soldering, reflow soldering, or conductive adhesives, such as anisotropic or isotropic conductive adhesives, ACAs, for example. Because the part is so small and so thin, it has a very low thermal mass. And you can see it here in the key properties in the center of this slide. The response time is very fast with only 100 milliseconds. It also has a high accuracy of 0.1 degrees C. And it's also very stable. So in storage or endurance and cycle tests that we performed, we only see a minimum drift referring to change of resistance over this time or over this test, measured after and before the test. Now, with that, I actually come to the end of my presentation. To summarize, I wanted to show you how RTDs work, some basics and fundamentals, and explain to you why a high resistance value is desirable and required, and what the conflict is that we are facing with going to smaller and smaller dimensions, and how we, with our latest innovation, the microRTD, are trying to push those limits. If you have any further questions about our standard products or our microRTD in particular, please do not hesitate to get in touch with me. My contact details are shown here or on the website of this conference. And with that, I'm at the end of my presentation, and would like to thank you again for your attention. Goodbye.
Thank you, Dr. Nick. And with that, we will go into our final networking break of the day, where we will be coming back in 30 minutes at 3 o'clock Pacific time for the final group of sessions. So I'll see you guys back in about 30 minutes.